David Smith here with another Flip Classroom math lesson. 3 tips before we start. Remember that you can adjust the playback speed if that helps you work through the video. You can also pause the video at any point to take notes or jot down questions. Lastly, you can turn on the captions so you can read my words go by on the screen. I'd like to take this video to introduce you to a famous mathematical constant. It's the number E, which is called Euler's number. Euler was a German guy who discovered E. Yes, and it is a number that's out there just like pi. So like I say with pi, if or when we find aliens in the universe, they will know about this number. It's a mathematical constant that appears in mathematics. It's called the natural base, and we'll talk about why that is in a minute. But first, let's take a look at one of the situations out of which the number E arises. So here's an exponential function. Here's our x, and our function is 1 plus 1 over x raised to the x power. So let's take a look at that. What happens when x is 1? We're going to have 1 plus 1 over 1, so that's 2 to the 1 power, so that's just 2. Okay, cool. Now what I want you to do is pause the video and let's put in 2 for x. What do you get out when you do that? So it's 1 plus 1/2 to the second power. So 1.5 to the second power. What does that give you? Okay, so here's what I get. When I put 2 in for x, I do my math on my exponential function here. I get 2.25 for f of x. So try 10. See what you get with 10. Okay, when I put in 10, I get 2.594. So now I want you to pause the video and go ahead and put in 100, 1,000, 10,000, and let's do 100,000 just for kicks. Is that 100,000? We need one more zero. There you go. So pause the video and do these 4 calculations, fill in your field here, and come right on back. All right, so check this out. As I increase my number, I'm going by powers of 10 now, from 10 to 100 to 1,000 to 10,000 to 100,000. You can see that my number is getting closer and closer to something. Notice how we're not increasing quite so much. We had 2.7, now we stay with 2.7 all the way up. Then we got 2.0, we got 2.1, now we've stayed with 2.1 all the way up. And finally we went from 0.5 to 7 to 8, and now we're staying with 8 all the way up. So as we increase this number, the first digits are going to stay the same. Those are digits of E. And as we hone it down, we're going to get more and more digits of E. So let's take a look at a definition of the number E. Okay, we're going to define E with a limit. So take a look at that. What it is, it's the limit as x goes to infinity. So what we're doing is we're just taking this number and we're running it up really bigger. So as that number goes to infinity, remember we can't get to infinity, but we can go to it. As x goes to infinity, this expression of 1 plus 1 over x to the x power, that equals the number E. Okay, so pretty simple expression. You wouldn't think that would generate a valuable and interesting mathematical constant, but it does. Okay, let's get a really good approximation of E. Now, E, like pi, is irrational. It goes on and on and on forever. So you can never write it down exactly. You just can't, because your last digit is going to round in some way. But if we put in 1 billion for x, that's one with 9 zeros, and we do 1 plus 1 over x to the x power, we plug 1 billion in for x in there, we get this number, 2.718281827. That's E to quite a few decimal places. Okay, so here's an approximation of E. Now, you probably have an E button on your calculator. You should be familiar with how to pull up E. If you don't have an E button, you're going to have something like a natural log or something on your calculator that you can use to generate E without having to type it in. Just like with pi, it's much better to press the pi button and get your calculator's best approximation of pi for use in calculations. So let's take a look at some of those. And I'm just going to turn you loose on these because I think you're going to be able to do them. Here's 3 calculations using E. So I want you to pause the video, pull out your calculator, and do e to the minus 3, find out what that is, do 2 times e, find out what that is, and do 5 times the third root of e. So do those on your calculator and come back. Okay, when I pull out my calculator, this is what I get. I like to simplify my exponents. We don't really know what e times itself negative 3 times is. That doesn't really make intuitive sense, but we have a rule of exponent that lets that put this term below the fraction bar with the 1 on top. So I can think about 1 over e to the third power. Did that on my calculator. I get 0.0498. This one is just twice e. So again, I pulled up e on my calculator and I multiplied it by 2. I get 5.44. That makes sense. If e is 2.71, that makes sense. Finally, this one is the cubed root of e. So I took the cubed root of e on my calculator and then I multiplied that by 5 and I got 6.98. So this little exercise here was just intended to give you a little practice manipulating and using e in calculations on your calculator. Let's play around with a function that uses e as a base. Remember, this is the natural base. So here's a function. This could be a population growth function, something like that. It looks a lot like one of those. And we've got basically growth as a function of time is 4,500 times e to the 0.03 t. So that's a time unit. It could be, like we could be looking at bacteria in a test tube. That could be hours or minutes. This could be years for a population. It could be decades for something to do with geologic processes. Who knows? But it's a time unit. So I've got 4 prompts for you. I'd like you to pause the video and see how far you can get. See if you can do these. If you've been following along in my class, you have all the tools right now to do this. What I'd like you to do is say whether the function is increasing or decreasing. You can tell just by looking at it. What is the y-intercept? Again, you can get that right from the equation. What is the equation for the horizontal asymptote? Again, comes right out of the equation. And then finally, once you have this information, I'd like you to sketch a rough graph. And I mean rough. Just use what you know from these 3 questions, sketch your graph, and come back. Okay, function is increasing. E is our base, and it's definitely bigger than 1. It's 2.71828, blah, blah, blah. So it's definitely bigger than 1, so we know this function is increasing. Wrote that there, a is bigger than 1. Second point, y-intercept. It's the constant that's multiplied by the base plus whatever is added at the end. Well, we don't have anything added, so the y-intercept is just this 4,500, or more accurately, the point 0, 4,500. That's our y-intercept. Our horizontal asymptote is just the term that's out here. So if it was plus 5, that would be the horizontal asymptote. But again, we have a plus 0 out there. We don't write it, but it's there. So the equation for the horizontal asymptote is y equals 0. Okay, sketch, super simple. I made my axes, my t-axis and my g of t-axis. I marked my y-intercept at 0, 4,500. I know the function is increasing, so it's going to go from the left low and on up. And I know the horizontal asymptote is y equals 0, which is the x-axis. So I just drew it right next to the x-axis, increasing up, going through 0, 4,500, and there you have it. And that's a perfectly good graph for that if the command is sketch. If it's draw, you probably want a few more points on there, a few more labels. All right, let's finish this lesson off with a quick peek in Desmos so we can compare. We're looking at the coefficient on the exponent term itself. And let's see what that does. Let's pop over to Desmos and take a look. Okay, here I am in Desmos, and I'm looking at our function up here on the left. I can see this is the function we just had on the whiteboard, and this is 4,500 times e to the 0.3x. See how we've got our curve. It's asymptoting out at the y equals 0 line, and right around, say, minus 15, it starts curving up sharply until it finally gets up here to 4,500, which is the y-intercept. So in case you're wondering, I did fix my scales on Desmos so it would show this graph. Otherwise, it's kind of hard to see the intercept and see a meaningful curve in here. So you want to be familiar with that. Now, let's play around with this function. I'm going to go ahead and put in a different version of pretty much the same function. Let's do y equals 4,500 e. And notice on Desmos, I just have to type e, and it knows what we're doing. It's not just e. So let's try e to the x. Let's just see what that shows us. And check it out. See how e to the x is doing the same thing. It's going through the same intercept, but it's much more flat and then suddenly curving. So this is like 1x, whereas up here we had 0.3x. So let's try one more. Let's just try like 3x. Y equals 4,500 e the 3x. And see how the 3x cuts it in even further. Still has the same asymptote at 0, 4,500. But now if I zoom in, you can see that this green line, this function, has moved closer to the origin. So it hugs the asymptote more tightly for longer, and then it comes up much, much more sharply. All I've done is, again, I'm over here on my left side looking at my functions. I've gone from 0.3 to 1 to 3. So I'm just increasing that coefficient on x. Let's just do one more. What do you think if I did 0.1? Let's do 0.03x. So 4,500 e the 0.03x. And as expected, let's zoom out. Check it out. That one is much more gentle. It's taking the curve. It leaves the asymptote quite a bit sooner and starts climbing. It still has the same intercept. You can see we're still at 0, 4,500. So it's doing that, but now it's coming up much more gradually. And so all we're doing is we're taking that exponent and we're multiplying it by 3/100ths before we raise e to that power. It's a much, much smaller power. So here's what's happening. The number on the exponent either increases the effect of the power or decreases it. So the bigger it gets, the more the power affects the value of the function. So if you're comparing it to just 1, then if it's less than 1, it's decreasing the effect. It's making the curve more shallow and more gentle. If you're increasing it from 1, it's making the curve steeper, the asymptote more. Okay, I'm going to go ahead and get rid of these three, and we'll just keep our e to 4,500 e to the x. I'm going to scroll back in a little bit so we can see that function more clearly. Let's take a look at a different switch. What do you think I'm going to do? 4,500 e, we didn't do something last time. We didn't try any negative exponents. So I'm going to go ahead and put in negative x. Check it out. We changed the function's increasing character, decreasing. That's all we did. And really what this is it's 4,500 over e to the x. That's what that negative exponent does. So it hasn't changed anything else about the function, except that now it's basically sort of mirrored across the y-axis. Same intercept, only now it's decreasing. And the truth is that if we now we change it to 0.3 or change it to 3x, minus 3x, it's going to change the function in the same ways, except that now it's a decreasing function instead of an increasing. So there you have it. Those are some attributes on the exponent that we just explored today while exploring the number e. Now that you've watched the video, take a minute to jot down notes or questions that you might have for our next class. You can also re-watch portions of the video that didn't sink in the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.